Okay, so we are ready for the next one?
Yes, please.
I realize I am the last thing between you and lunch, so it's not a good position to be. Okay, guys, so we have seen a couple of hardware presentations before. We're going to change gears. This is software related. And you may already know much of this, so if that's the case, sorry if I bother you. I brought my lovely assistant before the presentation. Hopefully you don't have to rescue me from any trouble that I get myself into. So I labeled this presentation Teaching New Tricks to an Old Dog. And this is about a summary of all the new modules or old modules that I have been tweaking for the 41. So it's all about the 41, right? So don't expect to find new technology, new systems. And also, I always like to trick the audience. So the very first picture has nothing to do with this presentation, okay? So if we are lucky, this will be next year's presentation, but not today's, as somebody says. I wish that was today's presentation because it's very exciting. It's about how to get to HP to communicate directly to CLs, right? So today we're going to be doing a summary of the tricks that I've been using on the 41 with CL, but it's not CL specific, right? So most of the presentation will be for anything you want, like Minder's MLL2K, which I keep using almost every week, and the software I use every day, well, every day that I go to my computer, right? That software, without your software, I wouldn't be here today, because that was really wonderful to do all the ROM stacking and undoing and redoing. And of course, Warren Forlow's B41 emulator, that thing is a blessing for encoders because it has the stop. You can just stop the microcode and go step by step. Really is fantastic. Okay, now, the agenda for today is, let's have a look at the library 4. Because we have heard about the library 4, and it's very simple, but we need to get that out of the way to understand what comes next. It's very simple, but it's very important to understand what it is about. Then we get into something called the sub-functions or the auxiliary FATs, and we will go about launchers, how to access the sub-functions which are available in the auxiliary FATs, and it can get a bit convoluted, as somebody was saying before, but it's logical, and once we also grasp the concept, we have no trouble to follow up. The last thing that I did was what I call the autocomplete. I think it was in 2003. I came to Allschwil to one of the meetings, from one of the early ones, and Mike from Stuttgart, Faulhaber, I think he's called Faulhaber. Right. He suggested something, it would be nice to have an autocomplete. So I type the first letter of the function, and then the machine prompts me some kind of solution. Like I type the F, and I say factorial. Okay, it would be nice not to know the spelling of the functions. So that's what I call the autocomplete. So you just type the first initial, and the machine comes up with some suggestion based on the install functions that you have on the machine that day. Then what happens when you add more power to your system, you also need more responsibility, how to manage the power. So I started having new sub-functions and sub-FATs and all these things, and I didn't remember how to invoke those functions and where they were located. So I needed to write something to be able to access them, regardless of where they were and what were they called, and that's what I call the universal execute. So we'll see that. And also, because now we have really big machines loaded with a lot of modules inside, and you have this bank switching and all these things, what I call the input-output bus can get very loaded, but the standard machine doesn't have enough functions to just navigate those things that you are adding to it. So how to load and how to interrogate the I/O bus. So that's the core of the presentation. And then we have another section which is, right, so what are all these modules about? The operating system extensions, emulators, simulators, replicators, and all these things. All right? And I have a lot of tables. One thing about the CL is that you have these 400 modules or 400 plus modules, but you need to know the ID, the IMDb ID. So you have a lot of tables in the presentation. You can refer to those by type, by the topic of the science, engineering, science, finance, whatever. Okay? And we will also get into one of my favorites, which is the formula evaluation module. Somebody mentioned the Texas Instrument 59 before. This basically is much better than any interpreter, even though you're using the old 41 to run your formulas on. But if you just type the formula and say evaluate, and the result comes up. Any questions before we begin with the agenda?
What is FAT?
Oh, function address table. Sorry, it's only the directory of functions that you have. And it's actually a great question because that's the content, not the next, but the one after next slide.
Okay.
So I'm going to start very slow. So in the beginning, God named all the animals, right? And also in the beginning, we had something called the page 4. The page 4, if you remember, if you were lucky enough to have the service ROM, you could plug this thing on the 41 and it takes over the machine. The operating system doesn't kick in, and the service ROM diagnoses the machine for you, right? The card reader, the printer, ROM 1230, etc., the display. But unless you're doing that, page 4 is empty. It's a waste of space, right? So the idea was, could we have something always loaded on page 4 that can be accessed by anything is around that you plug in there? So this is a dream for any programmers, because instead of putting the same routines in all your modules, you just have a library of routines, and that library resides in a place which doesn't take up any space. Unless, of course, you're using an HPIL module and you disable the printer, in which case that printer ROM goes to page 4. So there are some incompatibilities, but they are really corner cases. So most of the time, 99% of the time, 95%, page 4 is idle, is not doing anything. So if we can just put something in there, slit something in there, and make everything else use it, then we are saving a lot of space. The code is very consistent because there's no multiple versions of the same code everywhere. It's just one version, easier to maintain, and of course it's a savings in terms of space. So the idea of having the library 4 came up, and initially it was about routines, some math routines, some housekeeping routines. But as more functionality was being added, it was an ideal repository for the really tricky stuff, like the auxiliary FATs, directories, the extended catalogs, and also buffer administration routines. Buffers are these areas in memory where with some special modules put some information in there and nobody touches it. It doesn't depend on your registers or your extended memory. It's just part of the memory of the calculator that nobody else touches. Only the OS sometimes. All right, so what is going to be talking to the library for? On the left side of the screen, we have a set of modules which I call utilities or hackers or extensions that make use of the library 4. And you have the usual suspects. If you are green because you like the CL, you have what I call the Power CL Extreme. This is as a module with routines and extensions more or less directly applied to the CL. But that module is very big. It has 4 different banks. So inside of these big modules, you have sub-modules, even though you don't see them. So there you have page functions, extended memory, CL catalogs, and UMS. UMS stands for the Unit Management System. I'm sure somebody remembers that thing that HP came up with in some of the modules, like the thermal module for unit conversion. You want to change your BTU Rankine degree per pound into standard unit systems. So HP came up with something called the Unit Management System that was available in the thermal, in the machine design, and in the petroleum, 3 different versions. Well, I just consolidated the 3 and put it into the Power CL Extreme, and it's also available on its own module. But anyway, the idea of having these boxes inside of the big boxes is because they're large areas of functionality which are typically tucked away into different banks, because these guys are always bank switched. I think I'm getting ahead of myself. So we were talking about the library 4, right? So CL and the YREX module, which we talk about that later, are CL related, but they use the library 4. Then we have things like, I think there is a red LED somewhere here, right?
In the upper, yeah.
That one. Here you go. So extensions for alpha, utilities for RAM management, and utilities for MLDA M code writing. Also use the library for. The CCD module was a cornerstone, was a really seminal module. The CCD had the operating system extensions that Raymond Del Tondo extracted. Raymond is not here today. No. He extracted that part. Then I incorporated that part into the AMC, which stands for my initials, OSX. But in addition to the CCD catalog management, I added more stuff, like the HEPAX disassembler is there, and the hex editor is there too, and the AECROM, the programmers. It's staffed with all of things. We will see that later. And the latest kid on the block is what I call the Warp Core. And the Warp Core is also using the library for. So all these modules here are utilities, extensions, operating system extensions, and they're tricky, they are sophisticated. Every time I want to make a modification, I need to relearn the code because I don't remember how it works. And it's not simple, it's painful. But then we have the mathematical modules on the right side of the slide. And we have a few, like the complex support, the 41Z or Z, depending where you come from, the SAN matrix, and the SAN math. The SAN math and the embedded children, as I call them, the AECROM curve fitting, which was a real piece of work, solvers, time value of money, and solve and integrate. Solve and integrate was produced by HP, was adapted. Actually, it was an interesting story. HP hired another company to migrate the HP15's code on a different module for the HP41. And HP released the HP41 Advantage. We'll have a piece of that, right? So the HP41 Advantage is part of the Advantage module. I took that code and I put it into a bank. So I had to put it into a bank switched implementation, which was fun, right? I did the same thing with the solvers for the AECROM and the AECROM fitter, the curve fitting, which is also in microcode. And it took a lot of redoing and tweaking to wedge this thing and coax this thing into a bank. So the SAN math is perfect for the CL, but again, we are talking about a 32K module. 32K only has 8K footprint, so it takes 2 ports of the calculator, but each of these 2 ports has 4 banks, so it's 32. I'm not sure if I'm doing the math right. So the idea is, some users said, yeah, I love the SAN math, but I'm using Clonix or the MNDL or something else, or NovoRAM. Would you do me some versions which will have subsets of those? And that's what the thing on the right specify. So you have subsets of the SAN math, perhaps some of them with a bit more extensions, because every time I get into a code, I enhance it. So elliptic functions, areas, and series sums. This one is like a piece of a madman, is the inverse error function. If you are mathematically oriented, you know about the error function, about the inverse error function. And we are really getting into loony stuff. So I wrote this 8K ROM to properly calculate the inverse error function, which is paranoid. Solve and integrate, extended statistics, curve fitting, time value of money, blah, 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 blah. So what's the idea? The idea is that all these different universe modules use the library for. The library for, if you have a CL, is always there. If you have a Clonix or an OVRAM or Minder's MLDA2K, you can add it normally. You just have to put it on page 4. So that's all. Oh, I just forgot about the other two. And then I mentioned briefly before, I got together with somebody in the US, Greg McClure, and he's a good programmer, not like me, I'm just a hacker. And we did the 16C emulator. That was a challenging project, a 64-bit emulation of the HP 16C. Having a special buffer, so we got the 16C inside out, we didn't touch the code, we just did everything from the scratch. And we added more things on top of it. So this is a 16C on steroids, and it has the beautiful LCD display. It says the function names, you can program like using all the HP41 CL memory, etc. The latest addition to this pink area was the formula evaluation module, which is what you just get to type the formula in alpha with your parentheses, hit evaluate, and you can take the values from the stack, X, Y, Z, T, ZT, L, and also from 5 variables which are in a buffer, A, B, C, D, E. So you have 10 different variables, and you can use their names into your formulas, and the formula is calculated, and you can put the result of the formula in stack registers, the one you want. Okay. HEAPAX 4H is a version that I did, getting the original HEAPAX to work better on the CL. Like, HEAPAX is a very, very difficult beast to deal with, and I'm looking at Minder, because 2 days ago I just asked him something about the HEAPAX. So the HEAPAX, when they released the HEAPAX module, it comes with 2 special instructions that nobody understands apart from HEAPAX, the module itself. So to duplicate these instructions, you have to add some software. So there is software that adds those, supplements the lack of instructions on the CL. And that is in my HEAPAX 4H module. 4H is called 4H because it uses the library 4 and is revision H. So there you go, 4H. It also can disassemble itself, something that the HEAPAX didn't allow you to do it because they didn't want you to see their own code, right? But we don't have that restriction. Okay, here we go. So we all know about that, and if somebody doesn't know that, leave the room immediately. So we know that the modules, when you just stick in a module in your 41, there's something called the functional address table or the directory, which may have up to 64 entries. That's a maximum barrier. That's it. So the maximum number of functions you can have in a module is 64, right? The module takes 4K, and at the bottom of the module there's something called the trail or the coda, and there is some kind of identification. So it's 4 bytes that HP is putting there for ID or control. So what happens if you want to put more than 64 functions into a module? Well, you can't. That's it. Tough deal. You have to have another module plug into the calculator, etc. So nobody liked that. And the HEAPAX came with a good idea, which was the sub-functions. I didn't invent that, the sub-functions. The HEAPAX said, well, what if we could be able to just have another directory somewhere in here, and one of these 64 functions could be a clever one, a super function. And that super function could be accessing the sub-functions, the others. Simple enough, right? So that's what they did. They didn't do it in this way, and I will explain later. But that's the concept. Well, what if we add another directory somewhere? And by the way, we are not going to have this thing restricted to 64 functions. It could have infinite number of, depending on the available space. But you can have there 80 functions to 100. Then you need something here, because that's the only thing the operating system knows about. The operating system doesn't know anything about anything else. This is something like another construct that we have added, right? But if I have my super function, this super function may have a way to access the sub-functions in the auxiliary fact. And actually the super function is schizophrenic or splinter personality, because it can access the sub-functions by name or by index. Index meaning, if I have here 20 functions, I can say execute function number 5, 16, 20, the index, or I can type the function name. That's it. So that's all there is to it. But no, it's not. Because what happens now is perfect. But what if I add banks to the same page? So these are not new pages. So we are always on page P for page, right? Could be the page 8, 7, 9. What I'm doing is I'm adding banks to the same page. So the bus is getting a bit loaded. And then those banks can also have auxiliary FATs or directories, right? We're getting close to what the HEAPAX does. The HEAPAX did that, but it did more, because the HEAPAX added auxiliary FATs on bank 3, at the top of the bank 3, and in the middle of bank 3. That's what the HEAPAX had. Nothing here, nothing here, nothing here. So what you're looking at here is the biggest, fullest expansion of how many tables you can have into a 4-bank configuration. And I'm going to skip all the details, but all these things that you do, they are programmable, you can program them, you can just access them from your beautiful super function in here. So there is no more limits. You can have as many functions as you want, and you can stuff there as much code as you want as long as you have only 4 banks. The SAN math has 4 banks twice because it has 2 ports. Okay, questions? Is that clear?
Sure.
Are we all sleeping yet? All right. I know I had to say something here, I forget what it was. This is programmable, so you can have your super function into a program, and it can access any of the sub-functions, regardless whether they are in the main bank, at the middle of the space, or here in banks, bank switched banks. All right. Let's move on. Now it's where we get lost. Right, so in the beginning again, there were some very powerful modules released by different companies. We have W&W, they released the CCD. We have VM Electronics, they released the HIPAX. And we also have HP releasing the Advantage. Zen, remember his name? Sengrave, thank you. They released the Zenrom and the CPROM, and those guys were powerful, very powerful as well. So I have here a table which is, well, some of them had buffers. Yes, the CCD and the 41 Advantage had buffers. These are special areas where they put information and nobody else touches it. Some others had very powerful polling points access. I don't get into that. And some of them have the banks already, these things that I have here in green. So yes, they did. So you could, the HIPAX had banks, and on the CPROMs you could have bank switching. Okay? So this is not a new concept. The idea is, how about today? So today there is a list of special modules, and you can see also here by comparison whether or not they're using sub-functions, if they have banks, the bank switching configuration, if they have buffers. So you see that the table is getting more and more populated. That's the idea. Of course, now we are adding a new column, which is, do they use the library for? And all these use the library for. Okay? So you can get some really, real powerful stuff where they use everything. Like this guy here is a library for aware module. It has sub-functions, it has bank switches, it uses a service interrupt, the input-output interrupt, and it has 2 buffers. So everything happens at the same time. You're working in 3D or 4D at the same time. So it has all these beautiful features, and those things are needed if you really want to get over the initial design limitations. So some of the buffers, if you look at these, you will see that, for instance, buffer number 9 is used by multiple ROMs, which is also a novel concept. The idea of buffers is that, okay, I have my new nice ROM, and this ROM is going to have a private memory area. But now what I'm talking about is we have one buffer, which is there, and is like public. So different ROMs are going to go there and pick and put things in there as they feel necessary, because other ROMs are going to be checking what the first ROM did to see if they can collaborate amongst others. So that's the idea of having buffers which are used by multiple ROMs. Here's the example of buffer 9, somewhere here. Buffer 9 is used for the last function. So I put a number, I execute one function, and then I want to execute the same function again, but I don't want to retype its name. So I say, execute the function that I did last time. That's it. Regardless of which module put it there. This is the time where the audience gets lost already. Yes.
You have some way to distinguish which of the, what is the structure of that buffer 9? Is it?
It's very simple. It doesn't say that. Buffer 9.
Yeah,
Buffer
but
9.
you see what's there. Historically, each module had its own buffer, so it can control its own data structure inside. Okay?
Yes.
Now, if you go to the idea of having buffer 9 shared, but you have to have some structure or some knowledge.
Absolutely.
And then
some rules. Rules
sure.
of engagement, right? So you cannot step over somebody else's information. So each of the modules which access the buffer 9 knows which part of buffer 9 to use. So they all know not to delete it. If buffer 9 is there, okay, don't delete it, right? And then go to this register that belongs to me,
okay.
right?
So this is documented?
It is documented.
Okay.
It is documented, I think it's in the SAN matrix and also in the, not SAN matrix, SAN math and the library for documentation.
Okay, good.
Okay, it's just 5 registers because it can only have 5 last functions entries.
Yeah, but the buffer can be in
No, the buffer is only 5 registers long.
No, this for yours, but you can.
Oh yeah, buffer can be, you know, the whole memory.
Yeah, sure.
Like if some of you remember the 4th ROM,
Yeah.
that was the whole memory. It was a buffer, right? Never worked, but it's a beautiful concept. I wish that one worked. I spent almost 1 month trying to get it to resuscitate that thing, and I only got it partially alive. Okay, so buffer 9 is used by multiple ROMs, and some others like the buffer 5, when W and W introduced the CCD module, they introduced the buffer 5. When HP introduced the HP41 Advantage, they copied all the matrix functions from the CCD, so they continue to use buffer 5 for the very same purpose. Okay, and there's others. Buffer 6 is the formal evaluation. We will see a couple of those with some examples. Okay, so we're going to skip over that because some buffers are used for more than one reason. So they get double duty service, so to speak. But we're not getting into that. So let's start with the operating system extensions. So when you purchase your CCD module, you realize that you have more catalogs. In addition to catalog 1 for programs, 2 for extended ROMs, and 3 for your operating system functions. It came with catalog 4 for matrices, catalog 5 for buffers and alarms, and catalog 6 for user assignments. So what I did is I added more. In addition to the 1, 2, 3, 4, 5, 6, I added 7, 8, 9, 10, 11. So when you just go there and click the right catalog, you will see what it is. And the idea was to use that for some dedicated usage, like the complex stack. If you use the 41Z or Z module, you can have, and that goes into your presentation before this morning, Hans. The 41Z has a 4-level stack for complex numbers. So we're talking about 8 registers, plus another 2 for last X. It doesn't worry about the overflow, so if it overflows, it overflows, right? But you can always save that into the extended memory, and you can look at the extended memory files, which contain 41 complex number stack. Okay, another one's for polynomials, 4th code, HIPAX data, etc. So the idea was to extend the number of catalogs. Fine, so we did that, I did that, and it's shown, but also we wanted to put more stuff. So some of the utilities that came with the RAM box, also from the same company, W&W, I had the space, so why not pick them up from the RAM box and put them into the extended operating system extensions? So here we go. Compile programs, page utilities to replace the execute instructions, replace them with XROM instructions, etc. So they are there. Extend your prompts when you just go from 2 different fields to 3 fields, or from 1 field to 2 fields. And the page ROM checksums, all these things are not new, they were in different ROMs. All I did was just put them together in the same place. But then I did more stuff. I did a buffer catalog. Buffers are very elusive. So they are typically managed by some specific ROM. If the ROM is not there, when you switch on the calculator, the operating system says, well, somebody put this buffer there, the owner is not there, so I'm going to wipe it out. So the module who owns the buffer needs to be there, otherwise the buffer gets wiped out. So if you have multiple buffers in the catalog, I wanted to see how many buffers do I have, because the space is finite. I don't want to, I want to know how much space I have there. So the buffer catalog came into being. And other things like the page catalog. What do I have plugged into the calculator? So buffer catalog, page catalog, etc. Right, so this is what it has. Buffer catalog, and then I also put some sub-functions because it was not enough with 64 functions in the main fact, as we saw before, so I needed to have an extended directory and a super function that accessed the little brothers. Because I had space, I also added the AECROM program generator. Some of you may know that one. is there with its own overlay, so you can write programs just by typing the formula. It's not the same as the formula evaluation. It's not to evaluate the value. It's just to write the RPN program by itself. All right, let's move on to other utilities. These are the usual suspects. We have many people to thank for, because these are just putting it together into a nice format. But we have a new module, which is the alphabetical utilities, Alpha 4, the Rampage, the Toolbox, the XROM, etc., etc. If you want to program in M code, this is beautiful because it allows you to calculate the jumps, and it allows you just to put the number, the instruction directly, depending on which address you are trying to call. So when you are programming things on library 4, the beauty of library 4 is that it's always in page 4, right? And this may sound like a stupid sentence, but it's always in page 4, so you know exactly where your routine is. So you can call it by address, not by reference. All right. Dr. Jekyll and Mr. Hyde. This is the time when you wake up. So this was done before the extended directories were born. So the idea was, so I have these 64 functions, I cannot have more, but what if I just replace those 64 functions with another list of functions? And what if this replacement could be done automatically by the module itself? So that's what it is. So you have a function in this list, which is called Mr. Hyde. If you execute Mr. Hyde, what's going to happen? It happens that Dr. Jekyll, you're looking at Dr. Jekyll now, you call Mr. Hyde, the guy takes the thing, and it changes into a different directory. Of course, this cannot be done on a ROM, can only be done in RAM, because otherwise you're going to write on Flash or whatever. That was a very imperfect solution. It was not efficient. But it was a good beginning, right? And it was a very, very, very short way to do it. This is the code that it takes to do this, to change the personality of a module from type A to type B, okay? Very simple. But we didn't do that because, again, you need to have it in RAM, not in ROM. Read-only memory cannot do that. You cannot write on read-only memory unless you're using flash writing. If you are engineering-oriented, you will love this module, which is the unit management, how to convert from meters to parsecs, which we do that every day, right? So it was a great solution by HP, but it was lacking very fundamental units, especially for people like me, which I studied electrical engineering. So it didn't have anything about electricity, nothing, right? And it also, you didn't have any catalog, you couldn't just list the number of units you had. So I added that. I added more units, more dimensions. Prime numbers came into the equation here. And I remember doing that, and I wasn't aware of a paper that HP presented many moons ago about how this thing was developed. So I came up with the idea, there must be using prime numbers. And then after I do the whole thing, I read the paper and say, hey, we are using prime numbers. Okay, great. So I added more units to the electricity, so the volts, the amperes, the coulombs, etc. So you can type unit conversions like multiply coulombs times volts to convert that into kilowatts hour. So same structure, everything happens the same way. And then, what about tables? I mean, we're talking about HP41, right? So tables, there's nothing about tables. So I added a table with 20 units, and of course the characters are those characters that the 41 understands, especially the 41 full NAT, because it's the one that CL uses. But this is what you have there. From electron charge to the speed of light in the vacuum, etc. And also I said we need a catalog to see what are the units we have. Show me the units that belong to force or to temperature, to work, to electricity. So you go to the function, says show me the units related to electricity, and it lists volt, ampere, etc. The total recall, HP41 is introduced, and it has beautiful storage arithmetic. You can say store plus, store minus, but you didn't have any recall plus, recall minus, recall times, recall divided. So the total recall says, well, we need to overcome that limitation. So we have a new recall function that also can have mathematical, arithmetical functions. Puff. Done. But also add a new one, which is recall exponential. So you can say recall to the power of 5. Perfect. Add it to. But now that we add it, can we add more stuff into this module? Yes, we can add more stuff, and this is where it gets really confusing. Because I started adding more and more functions. So in addition to the recall special with the arithmetic children, if you want recall plus, minus, times, divided, you said, oh, we can also say, how about the stack? Can we add register comparison functions? Like, is x less or equal than y? This is normal function. Could we do a is z equals to t or equals to n in the alpha register? So that's how the dare to compare version was born. Not only total recall, but also I want to have a module with which I can do any comparison whatsoever. Any register to any other register to any value of the comparison. Equals, different, minor, etc., etc. We added more stuff like this shuffle, stack shuffle. You just have 5 prompts and you put the order of the stack register as you wish it. So from X, Y, Z, T, you can change that to any other order. You can zero them on the fly. You can also include registers from the alpha.
Why has it 5 on the scores?
X, Y, Z, T, L.
Okay.
Sorry. I wanted to have 5 prompts because no other function had 5 prompts. No, I was kidding. All right, so, and then I added more stuff like select case, right? I mean, this is an old clunker, right? Back to 79. Select case. I want to have a way to define one register as my special value or special variable. Similar to the recall indirect. Recall indirect is recall by reference. So I want to have, okay, let's make register 5, a very special one. I'm going to select it. And then I can compare anything else against the selected variable. That's what it does. And then you can do select case. Case 1, case 2, case 3, different flows of the program flows, which are a bit more modern, a little bit. Questions? So the total recall became as a total recall module, then it became the dare to compare, because it added all these comparisons. And then later, we're going to skip that because it's too detailed. Oh no, before I get to the later. Has anybody heard the sentence or the phrase, this is a solution in search of a problem? Well, this is what it is. Because what I did is, yes, I know that my recall function, I can recall a number, a register value. Recall 5, 7, 25, or I could use the gold key to say recall indirect. So I recall by reference. Give me the value which is stored in the register, which number is, as opposed to give me the value in register X, give me the value of the number, which number of the register, which number is in register X. So what happens if I press the gold key again? Just for kicks. Well, then the display changes into recall indirect double. So it's a double indirection. So give me the number, give me the value, which number is in the register, which number is in the register, which number is X. I'm lost already. Then you can press gold again, and you get recall double indirect, which is 3. Yeah, and you press gold again, and you get 4, indirect 4, which is 5, 6, indirect 6, which is 7, up to 10. So you can have 10 levels of indirection, which is totally nuts, right?
Not infinity.
No. Actually, yes, but it's actually as much as your memory allows, but the display only goes up to 10.
You need a lot of paper to keep the overview.
Yeah, what is it? Sivan.
HP75 assembly processor had this inside the CPU itself.
Really?
Yeah, and this is used for tables.
Exactly.
Okay, you have indirect tables and tables.
Yes.
You can have multiple, that was the Capricorn CPU, has a lot of indirections, instruction.
You get totally lost with this. It's impossible. You have to make your own lookup matrices, maps. So what the hell is the information? But it's Greg McClure, he wrote a sorting program using only the first 2 levels. So he used recall indirect 2. to do sorting without taking the values to a place to do the comparisons. You can do the comparisons there where the data is, right? And you can do the sorting. The stack is unused. That's one of the beauties. All right, this is really too technical, so I'm gonna skip it. The dare to compare, I know this is a 41 HP, which is, I don't know, 39 years old, but the user interface, sorry about this is not as beautiful as the 34, right? But the user interface is a beauty. So you say, okay, I want to do a comparison between two different directories. I start by calling the function. The function always gives you the X, or you can start at any register you want, either stack registers or alpha register. So say you want to compare Z and T. Then you would start directly here. Tick. You can come here with intention. But if you press the SST, that was moving you. Say you start in X. Here you say, I can say, is it equal? Is it less or equal? Is it less? This is just to do the swapping. Different, greater than or equal, and greater than, depending on your goal key. So this gives you toggles into this screen or that screen. Tick, 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 tick. Oh, it's not X what I wanted Y. Then you press SST, ping. Then this is the screen you see. So you can do the comparison between Y and something else, anything else. And as you keep pressing SST, you're moving down the stack, or up, whatever you want to call it. Then you get into alpha, and you can do the same comparison with the individual alpha registers and MOP. Then you go to Q, which is one of the weird registers you have in the first chip. The next one is S. S is that select variable. So you can select anything and compare that anything against anything else. The only first step that you need to do is first define which one is your select variable. And the last one is 0. 0 is the foster child. In other words, you can interrogate if any register equals 0 without moving the value from that register. Is register 25 equal to 0? Or is register 25 different from 0, greater than, less than? And it's all part of the same user interface. Tick, 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 boom. Smooth and flexible UI. I'm not trying to sell you anything, but it's nicely stated. Sweeps the whole range. You have 84 functions at your fingertips. You only use one user interface, which is quite nice. And it also supports indirect registers and indirect registers. So this is an example of what the select function works and how you can do that. You can select a register, or you can select any of the stack registers or any of the alpha individual registers as well, indirectly. You can also use the recall. The total recall also understands about the selected function, so you don't need to remember which one is the selected register. Just click recall, S, and boop, here it comes, because it's all interconnected. So that's the beauty of this thing, it's all interconnected, right? And the S thing is quite powerful, you know. Nobody has ever used it, but it's very powerful. You even can have 1,000 registers in your prompt, which is brutal. But when we thought it was all beautiful and great, something better came along, right? And if this is all, if you're going to remember something in this presentation, I would like this to be it, which is the autocomplete and the universal execute, the warp core. So here's the idea. The idea is, I don't remember how is this function spelled. I know it starts with W. So I want the machine to know, to be a bit more intelligent. Say, execute W and give me everything that starts with W. Anything, right? And I go SST, 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 and only those functions that begin with W are shown. Ding, ding, ding. Ah, this is it. That's it. Simple, isn't it? It is simple if you have these buffers that cooperate with one another and you have all this interconnectivity. It is beautiful and it's simple. So that's what it does. So you start with the execute and it tells you, okay, which letter please? A to Z or A to C. You can also put lowercase, you can put special characters, and there's ways to do all that, of course. I said, well, never mind, I don't want that. I want to use the standard execute. So then you press the program key and boom, it reverts to the native execute. Fine, I just go numbers, execute 25. You cannot do that from here because it's asking you for a letter, but then you just revert to the standard default execute. Or you can say, you know what, I know you are asking for a letter, right? But I'm gonna say, fuck you. I'm gonna type the fucking name. So I press alpha, and then I type the function name. And the function name could be anywhere. Like it happens the same when you type normal alpha. But this thing is beautiful because it also looks and searches for sub-functions. So if you use the standard execute, it only goes to the main FATs. What happens to those which are in the middle of the road or in the banks? They're invisible. But if you use this universal execute, which is check $, then it also finds your sub-functions for you. Okay? And then we have all these the powerful modules that I spoke about before. Where are the banks located, the auxiliary FATs, and what? You see, each of the modules has a super function that I told you about, but then I don't want to remember the super functions for all these modules. I want the mega giga function, right? And the mega giga function replaces all the super functions, and that's what the check $, does for you, the universal execute. That's it. A lot of fun to put all this together. So this is how it works in the navigation. I start by saying autocomplete, execute. So all right, A to Z. And then at this step, I can say, okay, you know what? I want to go back to my comfy area, which is the operating system. So I press program, was the only key available, and then back to the normal execute. Check 25, check indirect 3, or I just type a letter. I choose the L. I chose the L just for example, and it comes with LKA off, and it has nice different sign. Or I can do, I'm gonna press the divide key, and that's gonna ask me for a special character, like I want to put the angle, or the mu, or the left parentheses, or the right parentheses. I can also type the character code, which is not available by letters. I can press alpha for the universal execute, or I can press the dot or the radix for the last functions, because the 5 last executed functions are also stored in my buffer, so I don't have to repeat it step. If I did the L and I got the first one that it was found, I can do okay. No, that's not what I want. I know where you are. Jump to the next page or jump to the previous page. I do that with the plus or minus navigation keys. Or I do, oh, this function? I don't remember. Where are you? Give me some information about yourself. It tells me I am on page 6, I am XROM 5, 09. Okay, great. Or, you know, I made a mistake, it's not L, I meant M. So here I do enter, go to the next letter. Or shift enter, go to the previous letter. So I will just go back and start with N or whatever comes before L, which I forget. I say, you know what? I want to see all functions that begin with L. And I don't want to keep doing SST. So I do run stop. And it shows me one, the next. All of them starting by L until getting to the end of the bus and stop. Okay? Or of course you do SST, BST to go to the next function to the previous. And if you want to execute it, you just say X and it executes that function and it puts that function for you in the program and it puts that sub-function for you in the program, which is very tricky. Because sub-functions require the super function also to be associated with them.
One letter is missing. R for random function.
Random.
Yeah.
It's called...
If you don't know what you want to execute, you just
Hold
the R.
that thought. Hold that thought. We can see something similar later, but you're right.
He's not finished.
Yes. And then, if I go to the last 5 functions, which I did, it tells me, yeah, these are the last 5. You can go SST to see which ones are there, or you can introduce manually a new function into that buffer, which is very handy. So all kinds of crazy crap, right? This is if I haven't lost you already, this will do. You're all gonna go through the window when I go into this, but this is just for people who are interested in how the algorithm works. Because if we only have main FATs, this is dandy. This is easy. You know, I can start either in the operating system, which I have 130 functions, or I can start in any page I want, and the search algorithm goes sequentially. We're gonna go forwards. Right? Is not what I'm looking for? No, I'm looking for a W, right? Nothing here, nothing here, nothing here, nothing here. And I just keep sweeping all the bus, looking into the main FATs for functions that start with W. If I find it here, boom, I will stop here. Found one, show me, next. But we know already that this is not so simple. Life can be more complicated because we may have auxiliary FATs that the operating system knows nothing about, right? So we did, I apologize, this, I don't know how to delete that, but forget it, this is not there anymore, you are not seeing this, right? So what happens now is the search goes to the main FAT, nothing is found. Instead of coming to the next page, it checks for the existence of a auxiliary FAT in the same page. Yes, there is one, aha, so keep searching here. Nothing found, so you have to go back to the next page, of course to the main FAT. But it's not so simple, because some of these pages may have banks, bank-switched banks. So then the search really becomes crazy. You say, nothing found, nothing found, nothing found, nothing found. Oh, wait a minute, oh, this is really a paranoid situation, because the main FAT doesn't have it. Do we have an auxiliary FAT? No, but we have a bank, a second bank that happens to have one. Oh shit, so I have to just bank switch the ROM. Remember, we need to bank switch this ROM from a different place, which is my universal execute. So first you need to tell that ROM, you, bank switch. Ugh, well, I don't fucking want to. You know, only my master tells me to bank switch myself. No, I'm going to override your master, you're gonna do it. So right, okay, I'm gonna do it, fine, and drag my feet and do it. Your algorithm is looking for functions that begin with W, right? Nothing, Okay, so back to main FAT, back to the auxiliary one here. But what I mean, the main FAT also has banks here. It's crazy. And then the user says, oh, there is a back step button here. What happens if I want to go backwards, right? But then the algorithm says, not a problem. Of course, you need to know, you are not at zero, right? You are somewhere. You have been just looking for something. So if you want to go backwards, I don't know what happens here. This is just examples. This is the backward searching behavior. So now the arrows go the other way. And I decided that it was too complicated to take into account the banked FATs. So say, I'm not going to be looking for sub-functions in banked FATs, right? So going backwards, which is using the back step, is actually simpler depending on where you start. Of course, if you are looking at a function in a banked FAT, you stay there. So you go backwards, but then you're going to go to the normal auxiliary and main only. So this will be skipped, and it will go backwards. Anyway, try to put all that in microcode, and you're pulling your hairs for days and days over it. The other thing that I added to the warp core module, is support for lowercase characters into the alpha ASCII file editor. The 41CX comes with a new function, only 38 years old function, right? Called ED editor. And that function, you can edit your ASCII files directly. You don't need to use the append reg, recall reg, all these crappy functions. But the function, this editor doesn't support lowercase or special characters. Well, now it does. As simple as that. So you can type the lowercase characters or the special characters directly using ED editor. It's called now ED+. Okay? If you're implementing Jean-Francois' beautiful patch to see these lower characters on the half nut, you will see them directly. So you say, hello, mu pi, okay? And you just input the characters using ED+. Of course, you need a half nut machine to see them. You don't need a half nut machine to input them, so you can input them using any machine. This editor is in ROM 5 on the CX. It's a bank switched. So I needed to extract that out of the bank switch and put it into a different place. When you have something in a fixed location, as I told you before, like library 4 is always in page 4, the CX knows that the editor is always in page 5. So all the routine calls are simple 2-byte calls. This is now on a warp module, which you can plug into any different page. So you need to change all these calls into a 3-byte call, so it's a bit more complicated. Details. And now welcome to the shadow buffer. That's where things get shady. The shadow buffer is what I use for many different things, like the shuffle function to reorder, to sort the stack. But it's also used for other reasons, like having an emergency storage location. So you have 5 registers. More often than not, you're trying to program something, and I ran out of registers. So here you go, you have a buffer that's going to lend you 5 new registers. Or for these 5 variables that I told you about, A, B, C, D, E, that you can have in your formula evaluation ROM. It's called the shadow buffer because most of the time it's shadowing the stack, but it can also be used for other reasons. Back in the day, the modules that were available were only standard modules that didn't have any bank switching. The IR printer module came along and introduced another bank switch page. The CX, of course, had the CX system here as a bank switch. The HEPAX had 4 banks. HEPAX was a revolutionary addition to the 41 bus, to the 41 platform. For today, we are now into a real exploded situation. And this is just an example that nobody probably will have ever, but you have many different modules that have 4 banks or 2 banks. Like examples here are the 16C sim emulator, the HEPAX, which has been with us for many years, the advanced matrix, 2 ports, 2 pages, each page has 2 banks. The Sun matrix has 2 ports, each port has 4 banks. The Power CL Extreme, etc. So now when you have all that many different things going on, you need to be able to how to put things in there and to interrogate what's in there. So we added more functions. The first function, which was Gaius Iceni idea, actually the idea was a combination of many people, but I really credit him for asking me to doing it, is when I switch on the calculator, I may have different modules. If there is incompatible XROM IDs, I want a message. It's not like the Stack Overflow, but it's like configuration error. So I can pull a module out, put a new one in. What if you put 2 modules with the same ID? Then you're gonna have problems. So every time I switch on the calculator, configuration okay or configuration bad, because you have a duplicate ROM number 5 or 6 or 7. Okay, so that's what happens. This is the example of a configuration with different ROMs, so that's what it does. It just scans the bus and it makes sure that there is no conflicting or duplicate ID numbers for the XROMs. And then some other functions that ask about, give me a list of the XROMs that I have, give me a list of which of those ROMs are bank switched, give me a list of the free ports, free pages, give me a list of the busy or used pages, and that's it. All right, so now we have 3 slides on the CL. I'm just excited. Sylvain is getting very excited. The CL has a lot of RAM pages, 256 or to 512, depending on which version you buy. But 4 of them are very special. The first 4 in RAM. The first one is where the CL keeps the information that we understand, we all know as the HP41. The registers, the extended memory, the stack. But there's also 3 other blocks or pages, 4K blocks, that are empty, nobody uses them, and they can be used as, well, what if yes, I make a backup of the main machine? So I can have, boom, dump the contents of my machine into the 2nd or the 3rd or the 4th CL page or CL block. So the first incarnation of the module, which is called the expanded memory, you can think of these are expanded memory blocks, like the normal machine has main RAM and extended memory, right? If you were alive when MS-DOS came into the market, that was a horrible situation with your extended memory, expanded memory, and the drivers, and oh my God, it was unbelievable. So, sorry, I just borrowed the same names. Well, extended memory was HP's name, so I borrowed expanded memory for the CL blocks. So the first incarnation is just simply be able to back up the files or the information from the main memory to the CL expanded blocks. So you can do that completely or by blocks. Give me a backup only of the main memory, or give me a backup only of the extended memory, or the registers, status registers, or everything. But then I said, how about going to these expanded memory blocks and say, you know what? These are actually 1024 registers. I want to access each of these registers individually using functions like store and recall. So only they are called Y store and Y recall. Everything starts with a Y, like Monte, Monte's last name. So you can just type Y store and Y recall and Y not, and you put an input number. The index is a 3-digit input because you have, actually, yeah, I know I told you what, you have 1024 register, but you can access directly the first 1000 from 0 to 999. The others only indirectly. So this block has a double duty function. You can use that as a memory backup, or you can just have it as available memory with random access to each of these registers if you use the new registers functions, which is absolutely very valuable. Okay? I don't know why I put this in here. This circle, imagine this circle is here, right? And this is an example that I will dwell into later, which is how to use this expanded memory block with the matrix functions originally developed by CCD, by W&W. What would this be? Yeah, this is just an example of the Y functions. I don't mean Y as a question mark, but in Montel-Dalrymple. Y recall, Y store, Y ISD, increment and skip if greater, I DSD, decrement and skip if equal, Y view, swap X and whatever, but this X is X, and whatever is a register in the expanded memory area. So basically, why that many functions? Answer, you just get any program that you have written, and you just replace the recall and store with Y recall and Y store, and you don't have to convert the program. That's how you convert programs to use the expanded memory, replacing the original native functions with the Y functions. So no need to, rack your brains trying to understand how do I convert this program to use the expanded memory. Just replace the functions by name. That's the beauty of it. That's why you have that many functions. All right, I'm not going to get into the dark corners of this implementation. So what I told you is I got a list of programs which are available. I replaced the standard store and recall with Y recalls and Y storage, and I put it together into a new ROM which is called YREX applications. And you have the PPC matrix and block routines. What else? Random and sort blocks. All the famous Hall of Fame PPC applications are now available also on the expanded memory. Okay? More stuff, but really bad. All right, changing gears. No more CL now. We are back into the 16C. Anybody here uses a 16C ever? So the 16C was a difficult one to implement because the 16C can support up to 64-bit words, right? However, the 41 architecture has 56 bits registers. 56? It's 56. Mm-hmm. So, we're lacking 12 or whatever, I don't know. How many are we lacking? 14? How much is 64 minus 56?
12.
12. So we were lacking 12 bits. So Greg and I thought about that, and he came up with a beautiful idea, which is the Martin McClure buffer.
It's 8.
8. You understand why I need a calculator?
I need some calculations.
So he came up with a buffer, so we store parts of the values in the buffer. The first 32 bits are stored to the standard stack. The second 32 bits are stored into registers in a dedicated buffer, which is buffer 16. No, it's buffer, I don't know which buffer it is. Which buffer is this? Buffer 11. 11 hex, which is actually 16. So that's the idea. The idea is you have alpha. I remember Greg's sentence, alpha is your friend. So what do you mean? Well, you're going to input your digits in alpha, right? And then I will just transfer that information from the string, which is in alpha, into binary values, different stages, and these binary values are going to be stored as non-normalized, binary, as second half, the upper 32 bits of the values will be placed into the buffer, and the lower 32 bit of the values will be in the standard stack. So he said that alpha is your friend, I will take care of that. You need to take care of how the user is going to write the values in alpha. So that's how we divided the work. Divide and conquer, and it works quite nice. We produce a nice overlay, has a lot of, as you can expect, user interface details. You can access all the functions from here very quickly. One of the things I never liked about the 16C is that you have to be looking at the little 3s and 4s to see if you have a carry set problem or an overflow problem. So we implemented the training wheels mode. And in the training wheels mode, anytime your value, not the stack, but the value has a carryover, carry a set because it's too large for your bit size, your word size, it tells you, carry has been set. So it's a message that pops up and disappears, right? Beep, beep, and it beeps, beep. And if you have an overflow condition, you get an overflow, appears and disappears. Of course, you still have the flag annunciators here, like 3 is a carry set and 4 is an overflow. But it also prompts you about these values to let you know that, you're out of your bounds, you're stepping out of bounds. You don't have to have it. This only happens when you have the mode in the loud condition. If you put it into silence, or silent, you only see the flags as you do in the normal code, 16C. Apart from that, it's a beautiful, nice user interface because it's LCD alphanumeric. So you have the real information about what is your hex mode, either octal or hexadecimal, whatever, how many bits, you are in 1's complement, 2's complement, or unsigned mode, okay? And the user interface is also very interactive, so you can access many different functions from the same place, doesn't matter where you start. So you don't have to start from the scratch, you can navigate your way down and up, and there's launchers, because we have sub-functions, and we have these super functions which understand the sub-functions. All right, so I think that's enough about the 16C. The formula evaluation is giving TI a run for its money, because that's the idea. I want to type the formula, use the formula, the calculator will use the values that I have written into the formula, and it will calculate the value automatically. And that's what it does, right? It uses alpha, so your formula can be up to 24 characters long, but you can have multiple chunks of text. So you can do it by sections, and you can chain formulas. So the result of the first chain can be put into a register, and the second formula can use that register, so you can keep writing your formula in chunks. You may or may believe that, but 24 characters is very large for the standard formulas. We are using the 13-digit mathematical routines for the operating system, so the accuracy is quite nice. And of course, the speed is very nice because it's using microcode. Well, nice for this. Of course, that doesn't make any sense with the CL anymore if you put turbo 50, because everything happens like boom. You just do it, you get the result. What else happens here? So some examples. So this is the inverse sine of inverse cosine, inverse tangent of the cosine of the sine of x, which is actually x. One of the nice things that I like about this formula is that when you start opening parentheses, you end and you say, complete the formula for me. And then it counts how many left parentheses you have, and it adds all the right parentheses as needed. All right? What is the Neperian logarithm of the exponential of 1? Is 1. There you go. And the decimal logarithm of y divided by twice pi to the cube function power, or the beautiful square roots formula. There you go. Shuffle is also here. I like this function so much that I put it into the warp core and also here. Sort the stack in the order I want it to be. What is the order it is today now? Right now, of course, it's going to be X, Y, Z, T, and L, right? So I want that to be ZZ top, which means Z, T, O, P. O and P being from alpha. So you know what? I want to have it X is going to become Y, or Y is going to go to X. But Y is going to be 0. That's why I put a 0. Catch that, right? Z is going to be left untouched, and T is going to be O, and L is going to be 0. So not only I can just resort them or sort them in different orders, specifically specified here, but also I can cleanse them or clear them on the fly. This uses the shadow buffer that I mentioned before. Buffer 6, no more details. Along with the formula evaluation engine comes a module which has all these functions already pre-programmed for you. So these are using the formula evaluation. So if you look at the programs for these routines, you will not see RPN code. You will see text strings and a function which is evaluate. Formula, evaluate. And you can look at the list. You can have the gamma function, you can have the Lambert function, elliptic integrals, so they are not trivial. Meaning, the point here is that the formula evaluation is quite capable. Anybody here uses complex numbers? Great, we can skip these two next slides. If you did, you would like to know about these slides, you know where they are. Incredible module. As somebody said, some president says, believe me, incredible number. Okay, I don't say president. Somebody here uses mathematical functions? No. Well, if you do, you go to the Sun Math, it's 34K of code, staff, bursting through its seams. It has everything you wanted to have about mathematics is there. Different things, many different things. Also, the base conversions are there if you want. Anyone here uses matrix? This presentation is about to finish. If you did, you will come to the Sun matrix, because there you will have all the functions which you have available in the HP41 Advantage, which in turn is a recreation of the CCD array functions, plus big programs like determinant, linear systems, and inverse matrix. But here, also in the Sun matrix, you have more on top of the HP41.
What's the maximum size of the matrix?
Depends on which memory. I'm so glad you asked that. The maximum size of the matrix, if you were using the HP41 Advantage, I believe is 24 by 24, yeah? Because you're using extended memory. But if you're using, we can move to the next one. If you're using the CL expanded memory, you have 3 blocks of 1024 register, which is 3072 register, and you can go to up to 50 by 50. Now, that doesn't mean that you want to, but because you can, you will. Because imagine typing, this is an example of 30 by 30. You have 900 numbers to type, right? 900 elements to type. You don't want to do that in a calculator or a computer for that matter, because it's horrible. And this is not the way to deal with, well, if you have to deal with large matrices, typically these large matrices are sparse, so there's a lot of zeros all the way. And there's other algorithms to do that, right? But you can do that. I've done that. I didn't type the 900 elements. If you notice, this is what I call the anti-diagonal, which is all ones but the diagonal. And this is a great test case. And I made all these comparisons with Wolfram Alpha, and everything checked out nicely, squeaky clean, as they say, right? So that's the beauty. So you can have all these different registers. Now, the HP41 Advantage didn't know anything about the CL, right? Now, they did something beautiful. They is W and W. When they created the array functions, they did something transcendental. And I'm not using the words lightly. Because when HP introduced the extended memory, this thing that you see here clearly depicted is a lie. Extended memory is fragmented. There's blocks of memory. Like, remember, you can have the X functions, an X memory, another X memory. In between those, you have gaps, which you cannot address, you cannot access. So the extended memory has gaps in between. So the algorithms, when you're looking for matrix elements, you cannot just assume that they're going to be all sequential, because you can go in borders between modules, right? So that's tricky. So HP say, we have routines in the extended function memory. If somebody's crazy enough to delve into them. But then W&W, CCD says, our matrices, our arrays, can be placed either in main memory or in extended memory. They wanted to cover more customer base. So if you don't have X memory, fine, you can use your in your main memory. Or if you have X memory, you can have them either or. So they did that, and that was beautiful and very difficult. That code is very complicated to read. And what I did is, now my God, I have to add another type of memory, which is the expanded memory. Well, it's not that difficult, really, because they are all sequential. There are no gaps in here. So all I do is use similar algorithms to the main memory, which I know is small, but it's sequential. I use that and move it up to the expanded memory. What I did is I added catalogs, because when you have all that many space and you can have multiple matrices, you don't know what are your matrices. Let's say you have 2 matrices in your main registers. If you do a catalog 4, that only covers extended memory, but not your main memory matrices. Not anymore, because now we have a catalog for matrices in main memory. If you remember, they are in normal registers, so they're all R and then a number. So there is a catalog for main memory matrix. I also did a catalog for expanded memory matrices, which all start with the letter Y, of course, right? So in this case, it shows here that I have a 16 register matrix starting in the expanded memory register Y334. Okay? And it's very handy to know where your stuff is.
That means that you use 801, 802, 803.
Correct. Here, this is 801. The guy behind it is 802 and then 803. So even though your direct access functions, YSTO and YRecall, can only go up to 991, the algorithms for matrix can sweep the whole 3074 register range, which is this is amazing, isn't it? All right, we gotta leave off on something. Somebody here likes money? I don't. So there you go. So here you have the time value of money, which is the HP12C best known feature. I didn't copy the HP12C, I just I did a from the scratch implementation of the algorithm, which is very simple until you come to the point of the interest rate. And the interest rate requires that you use some kind of numerical method algorithm. I was lazy, so I used the Newton's method, but I needed to come up with a formula for the first derivative of the interest rate. Every time you ask people to give you that information, they say, this is mine. I'm not going to give you the information on how this is done. Well, here it is for you. Free access, this is the first derivative, and this is also the initial value that I use, the initial guess to calculate my interest rate. All for the taking and for the pleasure of having it available to us. This thing checks out very nicely. I just did all the examples in the 12C manual. You know Gene, right?
Mm-hmm.
He's a financial red hot person. He did also a lot of checking, and he says, it's okay. So I'm happy. And then I think we are done. The rest is just other things that you may be interested on, so you know where you have them. Extended statistics, curve fitting, elliptic functions, orthogonal polynomials. You know what we're talking about, right? This is beautiful. I also added some examples like induction coils or ellipsoids, the pendulum frequency that uses all these special functions sometimes if you want to do that properly done. Sums and areas, so single series, dual series, triple series, blah, blah, blah. Applications, combination of complex numbers and real numbers, so you need both modules together. They're here. Nonlinear systems, of course. Who can go in life without knowing the nonlinear systems? Runge-Kutta equations for differential equations and nonlinear systems. Recursive utilization of solve and integrate. So you don't see the message recursion on your screen when you're trying to use solve, a solve nest, solve within solve, or integrate within integrate. So it's possible, and it's pretty. Going from solve to solver, equation libraries. And there is 2 modules available with equation libraries. You just have the variables on top. You just choose which ones you know and which ones you want to know. One is the direct method, and the other one is called the using the formal evaluation module. I think we're going to get there eventually. This is where the presentation dies. Der Ausstand ist dritte. Dankeschön. The end is approaching. All right, so there are two different modules. The second one was done by Mark Fleming, another partner in crime. He liked the idea of the formal evaluation. The beauty of these things is, guys, is you get to know people, you learn things, right? So Mark Fleming chimed in and said, I love what you have done with the formal evaluation. This is better than Texas Instrument. Let me do something else. And he created the equation library. So using the formal evaluation module, you have your equations, input your knowns, and get your unknowns out of it. Very simple concept, right? I studied engineering, so I've been doing some programs when I was a student, and I did a revisiting of everything that I did. I put it together into a collection called the ETSII. And it has collection for mechanical engineering, electrical engineering, basically that's it. But a lot of things. Power systems, electronics, not much, but electrotechnics, which you relate to that if you are related to these fields. And then other things like are really lunatic frames, like orbital mechanics, which I really had a ball working on that because it was fantastic to learn what Kepler did X-100 number of years ago. The way he solved the problem that was unsolvable without computers, with the true anomaly and the real anomaly, elliptics and circles. These guys, they knew how to use their brains back then. I tell you, they knew it. Because now it's all computer power and algorithms, but these guys, this is still used. So I implemented both Kepler's way and today's, doing solve and everything at the same time. Anyway, all these kinds of things are available. You know where they are if you like them. Orbital mechanics, we're going to get. Now, here we go to the fun stuff. Somebody here writes the underground in your city. If you do that, you know that this is totally useless, but I did it anyway. Right? Because you all have your maps, and it's perfect, and nobody needs anything else. But so fucking what? I mean, this is so beautiful. I want to have a pathfinding algorithm that can be used in different networks, different subway networks. So that's what I did. And I implemented the networks for Madrid, the metro of my youth, Paris, London, Berlin, and New York City. Sorry I didn't put Montreal, but you can convince me to do that. Actually, I look at the
It's one
networks.
of my things that I have to do sometimes.
It's simple. I mean, simple means it's doable, very doable. The New York subway was a beast because it's way too long, and 3 different companies own that. Like everything in the U.S., right? It's not really done properly. So you have 3 different companies competing against each other. They have overlapping stations, overlapping lines. Sometimes you have to go from this chair to another one. You have to get outside and come back. It's crazy. Anyway, so that's what you have, the underground line. So don't leave home without it. And then some of you like Sudoku, so you can play Sudoku. This is Jean-Marc's Bellard implementation. Country and capitals. What is the capital of Kuala Lumpur? Haha, I know, it's here. And then dictionary, English and Spanish. I think it's about 520 words. Enough to get you in trouble. That's what I call it. So you can always just change between Spanish and English. It's not done. It's not done because, this is about the networks, the underground networks. The underground, you have all the nice amenities as you would expect, like list all the stations by line or list the stations alphabetically, connect to stations. Your computer doesn't like my presentation. I think it's quick.
It's too complex.
I doubt it.
Too much information.
Too much information, yeah? All right, so this could be a good moment, a good place to leave it. I hope it wasn't too boring. Some of you are still awake, which is good. I didn't fall asleep this time, right? Last time I did, I fell asleep. So that's where you have the information, and if you have any questions, ask Matthias.
Last time before you said he's a crazy guy.
Sorry. There are two crazy guys in here.
It's all a matter of interpretation. All right, thank you, and sorry for the...